I'm pleased to introduce our next speaker. She is at the very intersection of physics-based simulation and artificial intelligence. We will welcome Dr. Jing Bi. She is a technology senior manager at Dassault Systèmes SIMULIA and a specialist in machine learning, holding a PhD in mechanical engineering. Her work is tackling how we can accelerate doing high-fidelity physics simulation, and she is training deep learning neural network to learn from this simulation and then predict the results in seconds or even milliseconds. Imagine how we can get 3D results of an implantation test almost instantaneously. This game-changing work turns design cycles from months into hours. She is getting to explain this to us. Please give a warm welcome to Dr. Jing Bi.
Thank you very much. All right. So if you take a look at the 4 paradigms of scientific discovery, we started with observations and experiments. So we look at things, how things happen, and extract rules out of these observations. We started to build theories and universal laws to understand them. And then we went into the computer age. We started to use numerical simulations to solve some of the complex problems. Right now, we are at the age of data-driven machine learning and AI. We think there is a high potential in fusing numerical simulations that is rule-based and machine learning and AI that's data-based. My name is Jing, and I'm going to talk about non-parametric AI that's based on physics for engineering purposes today. I'm going to start with listing a few life science challenges, especially in the medical device industry. I'm going to talk about machine learning technologies that we're developing today at SIMULIA and the softwares that we're building towards tackling those challenges. We're going to show proven cases in different industries, including life science. And then we're going back to the challenges that we listed before to explain why we think that our technology is going to help and how it is going to help. All right, it's flipping. So when we look at the medical device industry, we identified 3 key areas where we think that the current method struggles to solve. The first one is the life cycle of devices. When we design medical devices, we want to predict its life cycle, and usually we do experimental durability test. That's very expensive and time-consuming. Alternatively, you can go with modeling and simulations. They're accurate and they're faster, but it still takes a significant amount of effort to build these models in order to predict. As another alternative that's built onto the modeling and simulations, we can use parametric AI to learn from simulation data, being able to predict in a much faster sense. But the issue is we cannot learn from historical database that's sitting there in our laptop and extract knowledge from it because they don't share common geometric parameters. During surgical planning, patients are very different from each other. We can receive imaging data that's very noisy or sometimes even incomplete. So in that cases, we still have to make accurate and fast predictions. The third one is how to scale from limited number of modeling and simulations to in-silico clinical trial for entire population and at cohort level. We can build for patient-specific models. We can calibrate it against the patient's measurement, but that takes a significant amount of time. So we can only do it for a small, limited number of patients. But in order for it to become useful at cohort level, we need methods to build these models very fast for a large number of populations. We think there's a high potential in using non-parametric AI methods that's based on physics to tackle these challenges. At SIMULIA, we started to develop and in this field to build neural surrogate solutions. So we started this in 2023, and we just released a first version of this product earlier this year that includes 3 different environments to cover parametric AI. We start with building a parametric model. We define the changing geometric parameters and its ranges. We define a design of experiment table so that we can run these simulations automatically to generate our simulation and machine learning database. We then go to the training environment. We pick our design variables that we need to learn from, and then we pick our solutions of interest to learn from. We train a machine learning model. We provide training environment monitors such as training and validation loss evolutions for you to analyze where is the training phase. Is it converged? Is the result validated? Once the result is validated, you can deploy the trained machine learning model in an iterative design environment. A designer who is not a simulation expert can take over the model and predict based on his new designs and get results in seconds instead of waiting for the simulation to complete. And then he can fastly iterate the design to come up with better designs. So that's all available in the current 3D Experience platform software. In SIMULIA, we always wanted to make sure that our technology is scalable and actually useful for different industries. So we built in our enterprise internal data set and models to cover different physics under different industries with different types of parameter input and different output. So these are some of the models that we built internally for us to help test our methodologies, improve our methodologies, and make sure that it works for different industrial cases. So it covers, for instance, from explicit dynamic analysis to static analysis, to fluid simulations, electromagnetic simulations, crash simulations, manufacturing simulation, and multi-physics simulations. We also want to make sure it works for different scales of models. We start with component-level models all the way to entire vehicle-level models. We want to support different parameters, geometric parameters, loading parameters, material parameters, etc. And we're also supporting different outputs of interest. It could be a 3D field that you're interested in predicting, or a signal that's dependent on time or frequency. We will show in the rest of the presentation some use cases here covering life science, consumer product, and automotive. So this shows our software interface that we have released for the parametric AI. You start with a parameterized model. You select the parameters that you want to build and learning on. You generate this DLE table. You can visualize the variations in the geometry of the designs and their distribution, and the result solution differences in the designs. Once you're comfortable with the database, you can start the training process on a GPU, for instance. After the training process, you can validate your prediction solutions against the FEA simulation results as a ground truth. Once the model is validated, a designer can take over, load the pre-trained model, and he can make design changes to this product. And then within a second, he can see some instantaneous feedback from the simulation results or machine learning AI result. And then he can iterate the design and in a very fast manner, comparing to before, because he has to wait for, previously he has to wait for the simulation results to finish. Now he just needs to wait for seconds for the neural networks to give us the result. So we automatically sort the candidate designs and find out the optimum design. This is a summary of all the steps that we went over in the video. So we review the design parameters and ranges, review the variations in geometry and solutions. We make sure the database is correct. We train, we monitor, we validate the training results. We deploy the model in a design environment. Now we're moving from parametric to non-parametric or generic representations of geometries. And why we're doing that? What's the benefit? With parametric representations, it is very concise. You have parameters to describe the variations in the geometries. It's a very concise and effective way to describe geometries. But the issue is, in real industries, we go from conceptual designs to detailed designs. It's very difficult to maintain that consistent chain of the design parameters. For instance, in the detail design stage, I want to add a component. I need to introduce new parameters. They're not consistent with my old parameters. And also, between different generations of designs, I want to really build innovative shapes. My shapes doesn't have the same physical parameters in terms of geometry comparing to before. But I want to train these models together. I want to combine these knowledge and learn from them. That's not possible. So you always have to build a new simulation database and training from scratch when you're designing a new generation of product. That's not effective. And you're missing all the knowledge you have learned in the past 10 years. So we're switching to the non-parametric representation of geometries. So instead of taking parameters, we're taking raw 3D data in the form of meshes, cloud points, or STL files. You don't have to even know the parameters. The machine learning will learn about the cloud points or meshes and extract a latent representation that describes the variation in the historical database. And then it learns the mapping from the geometric variations to the physics solutions. With that, we can actually take history of databases that's sitting there in our laptop or computer database that's sitting there for 10 years. I have 10 generations of design, hundreds of simulation data there. I want to learn and extract knowledge from there. We can build a foundational model by training all of the database together. And then we can use that knowledge when we're predicting the new generation designs. So that significantly helps us to generate enterprise knowledge and being able to accelerate new design explorations. We started to build this product in 2024, and we're releasing this product next year in 2026 FD02, which is about March timeframe. I'm working hard on that. So it's, thank you. So it also contains this 3 environment, which is the same as before, but it's different when you talk about data generation. You don't have to generate the data with parameters. You can just take all the designs from your historical database. You can just have the simulation object, which includes the model itself and the solution. We're going to support native results that's coming from SIMULIA simulation products, such as Abacus, CST, PowerFlow. We're also going to support external third-party data. So we're going to convert them into the 3D experience platform as a data set type on supporting this non-parametric AI learning. The second training environment is going to look very familiar, almost the same as the parametric training, but the underlying technology is very different. It's much more complex than before, and the training time can vary depending on which method we're using exactly. During the inference phase, you don't have to define parameters. You don't have to know the parameters. However you generate the new design, you just have to provide a mesh representation or STL file or generic representation of the design. And you get results instantaneously. So for these neural surrogates, we're providing 3 key technologies for our customers. One of them is the data analytics and confidence measurement. So when we're using AI, because it's data-driven and it doesn't understand about the physics laws, you're always not confident when you're doing the blind prediction. You don't know if the result is actually accurate or not. So we provide geometric and result analytics tools for users to train and understand the geometric encoding. So even they don't have the parameters, they can use our tools to understand the encoded latent space and compare the geometric differences between historical designs. The users can cluster groups of simulations together, identify the outliers, and do a better split of the training and validation on sets. Also, in the inference phase, when you have a new design, you want to know if I make a prediction with AI, is it going to be confident? So with this tool, you can analyze the distance of this new product comparing to your past product. How far is it? Is it within the distribution or is it very far? So how confident you are. We're going to give a confidence score so you can use the product with confidence. The second, which is the most important one, is multi-architecture machine learning methodologies. We develop methodologies building on top of the latest deep learning architectures, including, for instance, transformer-based architectures, graph-based architectures, neural operator-based architectures, and we support different types of input, such as mesh-based or graph-based or point cloud-based. We're going to release support for learning the 3D fields in the first release of the product, and we're going to keep working on adding more support, for instance, for time and frequency-dependent signals, as an example. And as always, we want our solution to be scalable for industrial applications. So we're really making sure that our solutions really scale to multi-millions of nodes and elements. We're realizing that by parallel computing and methodology improvement. And again, as always, we provide 3D visualizations across the entire tool chain. Now let's show a few concrete examples in different industries. So this is the car automotive industry. They always want to design their external shape in the conceptual design stage to minimize the resistance to the air when the car is driving. So that's going to save fuel. We're looking at, on the right side, the surface force prediction from simulation versus machine learning. On the top is from a power flow simulation. For one geometry, the power flow simulation takes 1 week on 100 CPUs to execute in order to get to this result. But once we train a machine learning model on it, it takes less than a second. And then if we look at the contour plots, which is on the right, we see that the correlation between the distribution and magnitude of the surface force is matching very well between the machine learning and the ground truth, which is the CFD simulation. We also do post-processing on this. We want to understand what exactly is the drag. Drag is the resistance in the actual direction that the car is subjected to, and we always want to minimize that. Because if you minimize drag 10%, that means you save 10% of fuel. So we integrate that predicted solution and find out one drag value for one design. On the left, you will find 1 point for each of the design. And if they lay on this 45 dashed red line, it means perfect prediction from machine learning against the simulation ground truth. If they're off, there's some errors. So for all the trainings and validations and testings, we found that for this use case, we have less than 1% error, even for the blind predictions. So that really helps our conceptual design engineers to, instead of wait for 1 week of simulation, they get a result in 1 second, and they fastly iterate to minimize the drag for their car design. So here, we see this new proof of concept interface that we're going to release next year. So instead of designing the parameters during inference and iterative design process, you would drag any candidate design's geometry into the input. You can visualize the input. You can look at the geometric variations. So here, our engineer is looking very detailedly to look at the tires, the mirror designs. Then you can load the pre-trained model. You can run the prediction. And within seconds, you get instantaneous feedback on the AI solutions. And then you can interactively play around with the predictions in the 3D visualization. You can look at where the resistance force is developed as you change the geometry. For instance, our engineers finding that there are some resistance force developed on this mirror, and a lot of them on the hood. So you can change the design, and you can iterate on the design. So you can, for instance, increase the hatchback, the windshield angles to improve the airflow behind the vehicle in order to minimize the drag. So our engineer is working very hard on analyzing this new design and running a new prediction using AI, and then looking at the new result. You can also put results together side by side to compare them and compare how a geometric change is leading to a performance change in the aerodynamics. So with that, as a summary, you go through 6 different stages in the inference. You import your newly designed geometries in different formats generically, such as an STL file. You can review the candidate geometry, and then you can import your pre-trained model. You can make a prediction, get a result in seconds. You can compare the design, and you can also do integration or post-processing to get other KPIs of interest. Here's another use case. We're still designing cars, but we're designing the car structures so that it's safer during roof crash scenario. So here, we're designing the B pillar which is the structure in the red boxes on the left. We're designing the shape of those B-pillars so it's more resistant to the roof crash. In order to see the difference, I have to magnify them because it's a large model and the variation in the geometry is local and very small. So it's really a challenging problem for us to solve in terms of machine learning methodology because we have to train the AI to automatically find where the changes happen between different geometries on a larger scale model where the change is very small. So with that, we show some results on equivalent plastic strain, which is an indicator of how material, where material is damaged, how much material is damaged. And on the right, the distortion, final distortion of the cabin, just to see how much intrusion it is into the passenger and driver cabins. So we see on the top the FEA reference as ground truth, and on the bottom, machine learning predictions for a new design that the machine learning AI has not seen. We see on the left that the locations of material damage is well predicted, correlates well with the ground truth, and magnitude is pretty well. And on the right, the deformation is predicted pretty well. Not only that, we also predict time-dependent deformation dynamics. So you can look at the entire event of the crash, how the deformation has happened. We're working with our collaborators at UIUC to test a new hybrid learning methodology. So instead of parametric versus non-parametric, we're combining and fusing them together. For this problem, we're representing the geometry using generic representations, but we're still using parameters to represent other parameters, such as material parameters, encoded length, and other physics properties. So it's a hybrid learning, actually. And here are our preliminary results of the 6 of the 60 testing cases. And on the left of each box is, on the left is the FEA reference, and on the right is the machine learning prediction. This shows the opening of the valve at the closing state. So if the valve fully closed, it's a healthy heart. If it opens, it's an unhealthy heart. And the open shape represents different disease type. So we can see that the pattern of the opening shape is captured pretty well here. Now let's go back to our 3 challenges that we talked about before. Why do we think that this software solution is going to help and how it's going to help? First of all, we think that non-parametric AI that's physics-based is going to help improve and accelerate the tier designs. How are we going to do that? So we start with collecting data from clinical cases and medical data. We work through our usual procedure to build virtual patient twin models. We calibrate those models and against experiments so that they are validated virtual twins. And then we use the non-parametric AI to learn from a historical database of medical devices. In here, it's a tier device. So you can train all past generation of tier devices on geometric designs together, including, for instance, the NTR type and XTR type and any past generations of design. So you build an enterprise-level foundational model that learns about all the past histories that is ready to make predictions for future generation designs. We think that's going to largely help us accelerate the tier design processes. No historical data is lost. Knowledge is extracted. No training is going to repeat it. The second one we talked about is surgical planning. So some of the data from medical images are incomplete, they're noisy, and how we're going to counter that with AI. We start with creating models from image segmentation. And we calibrate the model hemodynamics by tuning the parameters. For instance, left atrium pressure, we calibrate it against the experimental testings. We can also tune chordate parameters so that the valve dynamics is realistic. But when we apply these models to new patients, we don't know some of the parameters. So what we proposed is an iterative training and model improvement process that's in the middle here. So first, we train an AI model that's based on simulation model data and clinical data together. And then we make sure that the model is converged on available training data. And then when the new patients come in, we make the prediction and we compare on the measurable outcomes. Based on the error, we feed back to the model, physics model, and correct the model, tune the model, and iterate this process until everything's converged. So during this process, what we achieved is actually we have tuned the physics model against the new patient. So we don't have to do a lot of manual tuning. This process auto-tunes the patient parameters for us to understand the patient properties. Also, with the addition of a physics-based model here, we're grounding the AI model to constrain it with the physical rules. So the AI model that's trained is physics-grounded and more trustworthy and generalizable and reliable. Last, we talk about these scaling problems for in-silico clinical trials. With modeling and simulations, we can do patient-specific models. We go through the regular modeling stages, we do the calibration, and we validate the model as a ground truth virtual twin. But what we really need is a population model, meaning we have to generate all different combinations of shapes and variations that represent a large number of population at cohort level to really make it useful for everybody. So here, we can use non-parametric machine learning technologies to encode the patient geometries and properties in order to generate new designs that are different to the database, but within the distribution of the database. So with that, we can very easily generate a large number of models. And then we can use the non-parametric surrogate model to make the predictions. So we're really making viable and efficient solutions at the cohort level. As a conclusion, we believe that with a combination of parametric and non-parametric AI, we're able to decrease the product development cycle from weeks into minutes. We're also going to expand the coverage of data sets from parameterized data sets to any historical database. So that's going to open a lot of more opportunities for us to apply AI models to. We're also increasing the credibility of these AI models by grounding it and constraining it to the physics law and physics simulations. So altogether, we believe non-parametric physics-based AI especially can bring to the new to bring precision medicine to a new level. As a conclusion, we cannot do this alone. We're a software company. We have our knowledge. We have our technologies. We build them into our software. But what we really want is that for it to become useful for your individual cases. You have your expertise and knowledge, and you have particular problems that you're tackling. We are looking forward to working with you to unlock the full potential of AI. Thank you very much.
Thank you very much. Is there any question from the audience? No? Oh, yeah, we have one question over there.
Thank you for the presentation. Very nice. I had a question about prediction. In case of multi-parameter or multi-process design, I get the fact that latent space can produce an ML solution that matches a full 3D DNS. In case of although history, essentially something has a time dependency between 0 to a final time, and I fix my prediction at time t, would you be able to trust this process to actually produce essentially a prediction of t plus some future time using an ML solution that can then go back and check whether it matches a pre-existing time sequence you had from a physics-based simulation full scale to see whether ML now can do also forecasting and not just validation that the current state has been, I guess, validated?
Yeah, it depends on the technology we're using. We're providing multiple technologies to handle these non-parametric AI cases. Some of them are transformer-based. Some of them, for instance, are LSTM-based. Some of them are graph-based. So depending on the technology, in some cases, we only look at a certain time range, and we look at interpolating within the time span. But for others, we use autoregressive and other transformer-based methods to make future predictions. So yeah, so it depends on which method you use.
Thank you very much.